Yes, sir. Yeah. Everything that's on my screen is being recorded. No, I shut that off to do this, yes. Okay, so we are indeed recording. Everybody's logged in. It looks like 20 of you. That's enough to get started. Okay. If Pear Deck crashes, folks, please don't alert me of that. Just either re-log in. Always just jot down that login code when you first walk in. If it crashes, I don't need an announcement that it crashes on you. We can still function without it. Okay, just kind of old school at that point. So I told you this is going to be a review section. So was Chapter 1. I was going to assign Chapters 1 and 2 over the summer. I decided to just do Chapter 1. I thought 2 might freak kids out, and then they might drop, and it would be really silly to drop for basic chemistry. Okay, so we're going to fly through this. We'll take formal notes. I'll give you a test. It'll allow you to get more accustomed to the way the classes run. So here we go. So looking at matter, we understand what matter is. We know that's defined that anything that has mass and takes up space, everything matters, right? Even the air around us. You guys have like 4 elephants worth of matter on top of you right now, whether you know it or not. We're all like supermen here on planet Earth. If we were to go to like another planet with less matter in its atmosphere, we could probably jump up a mountain, right? If you just think about going to the moon, how far you can jump because there's less gravity, less matter on top of you, okay? So it exists in 3 basic states. I was just referring to one as a gas, right? The atmosphere, things of that nature. A solid, liquid, and gas. This should be like super review from physical science. Okay, we're going to blow through basically every subcategory of chemistry today. So if you've had like academic chem and organic advanced, this is going to be way below you, and that's okay. So matter exists in 3 states. All matter, both living and non-living, is composed of elements. We understand that elements are the basic, simplest form of matter that we believe can exist, although now we understand that there's parts of the elements, whether it be electrons, neutrons, and protons. But looking at how they're organized into things we can actually refer to in science, the element is the simplest form. So it's a substance that cannot be broken down into substances with different properties, and it's composed of one single type of atom. I know you understand that. That's the whole periodic table of elements. There's 6 elements, though, that make up 95% of the body weight of organisms. You do need to know these. I remember them as N-CHOPs, no-CHOPs, SHNOPs, however you want it, CHNOPs, I don't know. If you have a clever way of remembering this, by all means, share it with me. But I always just have taught it in the past as N-CHOPs or SHNOPs. So carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are those 6 elements that make up most of what we are. And those are the ones we're going to focus on in here. And the cool thing about them is if you look at the periodic table, they aren't that complicated of elements. If you had me for biology, you remember doing bonding, and they're all in those first 3 or 4 rows, right? And so they're not very big, which makes it very easy to organize their electrons. It makes it very easy to play with bonding. Even if you have to draw the whole electron spectrum, it doesn't matter because there's just not that many. And really all we care about is that outer valence shell. And so not that chemistry is not important, but when we're looking at basically what we are, we're very simple when it comes to chemistry. We're not that complex. That whole bottom part of the periodic table, that's for people with suits in labs. The other stuff up top won't hurt you. We're made of this stuff, okay? I mean, some of it can if you put it together the right way, but you get what I'm saying. So we're really simple. That's why I say I only care about the top 4 rows on the periodic table. Everything else is for chemists. So an atom is the smallest part of an element that displays the property of the element. An element and its atoms share the same name. They're composed of subatomic particles, protons, neutrons, and electrons. Protons are positive, neutrons are neutral, and electrons are negative. Very good. Which ones do we bond with? Electrons. So there's a central nucleus. That's where most, I should say, of the mass is held. That's where you find protons and neutrons. So if I ask you what makes up the mass, you tell me protons plus neutrons. The mass number, I should say, right? So if I were to ask you, can you have a portion or part of an atom, I'm sorry, I said that wrong. If I were to ask you, can you have part of a subatomic particle? What would you tell me? You all have Pear Deck open, right? If I asked you, can you have part, like half or 2/3 of a subatomic particle, can you do that? Yes or no? As soon as I have 20, I'll stop. Who was able to use Pear Deck with me last year a little bit? A few of you, okay? So if you had me like a year and a half ago or whatever, you probably didn't see this. So 4 say yes, 16 say no. 4 of you are wrong. Okay, you cannot have part of a proton. You can have part of a neutron. Okay. Well, no. You cannot exist. Let me rephrase the whole question. You cannot exist as a proton missing any part of, let's say, a quark. Or, yeah, you guys are reading into it. If you read into an AP test like that, you're going to be wrong. Don't do that, okay? So you knew where I was going at, but yes, I know you're smart enough to know. You cannot have part of a proton. You cannot have part of a neutron in an element or an atom. Let me state it like that, okay? There are parts of them, but you cannot exist as part of one and still be a proton or still be a neutron. So that's why inside of the actual nucleus, that's where the mass consists. So you can never have, let's say, 15.9994 as a mass number. That can be your mass, right? But it can't be your mass. So why on the periodic table do I have these masses in decimals? Yes? Yeah, very good. And a lot of you had chemistry, so you understand this. These are averages of all of the isotopes of that particular atom. So they are not representative of any one isotope or of any one element. You guys get that? All right. It's very important to understand. So if I, for any particular isotope, want to figure out the particular mass number, not the atomic mass of that element, what do I have to do? Add protons plus neutrons. And it will never be a decimal, will it? Because the mass number is a whole number, right? Now, even rounding the mass number on the atomic number on the periodic table to the closest mass number, that's not even an accurate way to configure it for that particular isotope, is it? We'd have to know which isotope we're talking about. Okay. All right. So looking at the center, we know that's where we find protons and neutrons. We find protons in the nucleus. We find neutrons in the nucleus. That is where that mass comes from. We know that protons give us a +1 charge. Neutrons have no charge. So if I did not have any electrons, my overall charge would be 1 here. Generally, that's not possible, though. So if you have 1 proton, usually your negative electrons are going to equal that. If I want to know how many electrons I have, what do? I look at the number of protons. How do I configure the number of protons? I look at the atomic number. Okay, see how fast we're flying through chemistry? We have to review it. It's part of the curriculum, but we're going to do it very fast. So each element is represented by 1 or 2 letters to give it a unique atomic number. H, hydrogen, Na, sodium, C, carbon. These are the atomic symbols. Often in biology, we like to use letters or symbols that are not on the periodic table as functional groups. Anybody ever, do you remember R groups? Where do you find R groups? No? I'll give you a hint. You find them on the things that make up proteins, amino acids. Each amino acid will change which of the 20 different amino acids is by its R group. Look on the periodic table. Do you see R? No, there is no R on the periodic table. So often, symbols are not just elements on the periodic table. If I need to add something to a molecule, I might give it a new symbol or a new name. So the atomic number is going to be equal to the number of protons. We talked about that. And if you know the protons, you know the electrons, right? Because P equals E. Okay? Positive equals negative. And the mass number of an atom is equal to the number of protons and neutrons in an atom's nucleus. Now, if I know the mass number and I know the number of protons, because it's on the periodic table, can I configure the number of neutrons then? Yeah, basic subtraction, right? So if I want to figure out how many neutrons I have, I subtract protons, my atomic number from my mass number, the atomic mass rounded to the nearest whole number. Okay? If any of this is like blowing your mind right now, you need to come see me at lunch, and we'll sit down and go over it. I wouldn't ask you to raise your hand right now and go, I don't get it, but please come see me. So the atomic mass is approximately equal to the mass number. Now, I'm going to give you a problem. So let's say this is my atomic mass, okay, on the periodic table, okay? And let's say that this is my atomic number. How many neutrons do I have? Don't say it out loud. I know this is a fairly simple problem. Don't say it out loud. I'm going to take these off right now. I'm going back. So 3, 2, 1. What would my number of neutrons be? What was the problem again? I'll go back. This is my atomic mass. This is my atomic number. What would the number of neutrons be? Don't talk out loud, please. This is the atomic mass. This is the atomic number. Please tell me the number of neutrons that this element would have without talking out loud. You have 30 seconds. Some people never grow up. Yes. Okay, let's see what we have. 13. Oh, come on now. Be brave. No, I'm not going to find out who you are. I could, but I'm not going to. I'm not going to, like, post your name on the thing unless you write something inappropriate. 3, 2, only 15 brave souls out of 20. All right. It's not that hard. It's kind of simple. Shouldn't say that. Now you feel bad. All right, here we go. All right, I see 7.7. I see 0. Impossible. Can't be determined. What? What? Oh, my goodness. Oh, dear Lord. We're going to... Oh, there we go. Who did 8? Yay. Okay. So I gave you the atomic mass, okay, which is like off the periodic table. I even used... I used the number in this case close to oxygen. I just made one up, okay? So you should have rounded that to the nearest whole number, which for 15.8 whatever was 16, right? And then I told you the atomic number was what? 16. Oh, I did. Yeah. Oh! Oh, I better not use that recording. Oh, dear. I meant to put 8. I'm sorry. Oh, dear Lord. That's all right. That's the first mistake I've ever made. All right. Yeah, right. I know. That's a lie. All right. Well, shoot darn. Okay. I meant to put 8. That's what happens when you do things on the fly. Okay, so let's just walk through the next one now. Chalk that one up as a boo-boo. I was like, these guys are way too smart to be wrong. I must have made a mistake. I knew I did right when I saw the results, and I just couldn't figure out what it was. All right. So if you round like you all knew you were supposed to, that mass number to the nearest whole number, and subtract the number of protons, which we know is the atomic number, you should get the number of neutrons. If I ask you the number of neutrons for this carbon molecule up there, what would it be? 6. Okay, because you subtract 6 from 12. Is this an isotope? This is an isotope. Oh, don't give me the chemistry version of an isotope, please. In biology, we do not refer to isotopes in that fashion. Is this a radioactive isotope? Let me rephrase it. Okay, no. Okay, I know. Chemistry has warped your brains. The real world refers to isotopes as any time the protons and neutrons are different. Okay, that's how all geologists use them. That's how biologists use them, because they use them for radiometric dating and pharmaceuticals and medicine, and they are not usually referring to them in the chemistry fashion where everything's an isotope. The real world does not function like a chemistry textbook. Okay, everybody else says that an isotope is when protons do not equal electrons. On your AP test, do not try to correct the test and say you're wrong, that's not an isotope, because they're referring to a different number of protons and neutrons. On the MME, or the MEEP test, that's the way they're going to test you, unless they're referring to very specific chemistry, which usually they are not. Okay. All right. I wish that was not taught like that, but it is. All right. Because when we refer to radiometric dating, you better know that we're referring to one as a non-isotope and one as an isotope. So atoms of an element are arranged horizontally by increasing atomic numbers in rows called periods, and atoms of an element arranged in vertical columns are called groups. Now, atoms within the same group share the same bonding characteristics, so we say that they are what? In the same family, right? So in biology, we are very fortunate in that we don't need to worry about certain orbitals, okay, which makes life very easy. We generally just worry about 1, 2, 3, 4, 5, 6, 7, 8 families for the basic elements of life, right? Because NCHOPS, right? Nitrogen, carbon, hydrogen, oxygen, phosphorus, sulfur. That's it, right? Those all fall in those top 8 families. And that's why in biology, that's all I deal with. That's all I have to deal with. What is it?
I was just talking about how I got myself wrong on chemistry.
You got what?
I rounded chemistry, and I rounded myself wrong at chemistry one time.
Oh, you rounded it.
It was 32.06 something.
6.6? Yeah.
And I rounded up to 0.
Oh, no, because of sig day, yeah. Oh, yeah, that's another chemistry thing. Significant digits. Oh. And the real world does not use them, I'm here to tell you. No. Very seldom in even a chemistry lab will you use significant digits, which is very ironic. All right, so atoms we know shown on the periodic table are electrically neutral. Okay, that's why they're on there. Therefore, the atomic number tells you the number of electrons as well as the number of protons. So the elements you see up there are neutral. We know elements don't always exist as neutral components, but up there they do. That's representative of a neutral element. Because of that, if I give you the number of protons, you know the number of electrons. So we just went over this, but you understand that our rows obviously are referring to orbitals. We don't need to get into that too much, but when we look up and down, we're looking at the families, bonding, relativities, or who is related in their bonding capacity by valence level. So isotopes, you guys, are atoms of the same element that differ in the number of neutrons and therefore have a different atomic mass. And some isotopes spontaneously decay. Radioactive isotopes give off energy in the form of rays and subatomic particles, and they can be helpful or harmful, depending on what they are. There's a whole field of radioactive pharmaceuticals in medicine. They help destroy cancers. Sometimes we can use them just to track and image things. I remember my grandpa had to have an injection of radioactive isotopes, and it went through his bloodstream, and they were able to take a very accurate image of his heart to find out if everything was working right. But nobody could use the same toilet as him for 24 hours because he has to exude off that radioactive product, which is kind of gross and cool all at the same time, right? So there are benefits of isotopes. Imaging is one of them. Has anybody had a bone scan done ever? Yeah, okay, so bone scans, I believe they use a barium solution, which is an isotope, and they have of barium. Everything's an isotope, I know. And so you take that, but you see how it's not? The real world does not think of isotopes like a chemist does. Like when I say isotope, I'm talking about an unstable, different number of neutrons and protons, okay? So carbon exists in 3 basic states, and we use carbon, we know, for carbon dating, right? We've all remember that. Is carbon the only isotope we use for radiometric dating? No. Carbon is like only good for 10,000, maybe 20,000 years ago. Do we carbon date things like dinosaur bones? Those are 65 million years ago, but we don't use carbon, do we? We use a different isotope, don't we? We use radioactive dating. So this whole periodic table, you guys told me, it's chock full of isotopes, right? They're all isotopes. So I can use anything off of here to date something, as long as I can actually track it and track its half-life. Sometimes half-lives are so small we can't track them, though. But most of these have a very specific and very accurate half-life, just like carbon does. So carbon, there's 3 basic isotopes, 12, 13, and 14. If you were to ask me, not your chemistry teacher, which of these is not an isotope, what would I tell you? The first one, right? Carbon 12. Okay, that's a very stable carbon molecule. And these other 2 would be the ones that we refer to as isotopes. So electrons and energy. Energy are attracted to the positively charged nucleus, thus it takes energy to hold electrons in place. So if I bond 2 things together, is that taking energy? Yeah. If I'm going to pull 2 molecules apart or 2 elements apart, does that require energy? Yeah. So what you're saying is anytime I make or break a bond, energy is involved? Yeah. So it takes energy to push them away and keep them in their own shell. And the more distant the shell, the more energy it takes to hold in place. And electrons have energy due to their relative position or their potential energy. And electrons determine chemical behavior of atoms. We know that. The electrons in that valence shell help determine how elements are attracted to each other. The ones on the inside do too. We know that. But the ones on the outside, that valence shell, the ones that are exposed to everything around them, are the ones that are going to determine how those molecules behave or elements behave. Don't worry, guys. We aren't going to blow through everything today. I'm going to pause and we'll go over a few things in a minute. Now, the Bohr model, which a lot of you are familiar with, is a useful way to visualize electron location. So that'll show all of the electrons in that particular element. The electrons revolve around the nucleus in energy shells, and for atoms with atomic numbers of 20 or less, the following rules apply. So notice I said 20 or less. So we go to the periodic table, and we find calcium, and we notice there's a different orbital that starts after that, right? In biology, will I ever really have to worry about anything above 20 for the actual what we're made of things? The most we won't, okay? So all the rules I'm talking about apply to the first 20 elements. Now, I don't tell you that in regular academic biology, but I usually am using the ones in the top 20 in all of the covalent bonding activities we do, right? Okay. So thus rules cover most of the biological significant elements, most of them, not all. But the first energy shell can hold 2 electrons. We know that. That's why you have 1, 2, and then we go to the third row. Each additional shell can hold up to 8. Up to 20, this rule applies. Okay? And each lower shell is filled first before electrons are placed in the next shell. So you cannot move on to another level until we fill the first one. So you have to fill 2, then 8, and so on all the way up to 20, up to the 20th element. So the outermost energy shell is called the valence shell, that outside shell, and that's the shell we bond with. We understand that. And the valence shell is important because it determines many of the atom's chemical properties. The octet rule states that the outermost shell is most stable when it has 8 electrons, except if an atom has only 1 shell. The outermost valence shell is complete when it has 2 electrons. Why don't you guys tell me the 2 times in that first 20 elements where this octet rule will not apply? It's only 2 times. There's 2 elements where this octet rule will not apply. Please type it into Pear Deck. Thank you. You can use their symbols. I don't care. What are you doing? What are you doing? What are you supposed to be doing? Okay, what happens if you sleep again in class? Okay, I know you know this stuff, but I have to actually cover it. It's part of BP Bio. Okay. 9 responses. Oh, there we go. In 5, 4, 3, 2, 1, 3/4, half, no. All right. Helium and krypton. Okay. Hydrogen and carbon. Xenon and neon. Air, okay. Carbon. I like hydrogen and helium. That's what I was after. So I don't know where carbon came from, but I like hydrogen and helium. So hydrogen and helium, right? Hydrogen has 1 in its outer shell, so it's only that first energy level there, so it's only going to hold 2, right? Okay, so it's almost full. But then helium is part of the noble gases because it's full with 2, right? So those 2 don't follow octet, okay, for bonding and for everything else. They follow the duet, we'll say, okay? So it's like a duet and then 2 octets. Sounds like a symphony. Sorry. I can do better than that. Worse than that, right? Yeah, okay, all right. So looking at the valence electrons, the number of electrons in an atom's valence shell, where the shell determines whether the atom gives up, accepts, or shares electrons to acquire 8 electrons in that outer shell. Atoms that have their valence shell filled with the electrons tend to be chemically stable. So if I look over at the periodic table and I understand that I have a duet and then a bunch of octets in that first 20, we can understand that helium has a full outer shell, and so does everything here with a rule of 8, right? Octet, so they're full. And we won't talk about anything over 20. Okay? So understanding that, these will or will not bond. Everybody, what do you guys think? Will it? Well, we don't need to do paradigm for this. Will they bond with anything? No, they're noble gases. In biology, I always say they're noble. They're kind of stuck up, right? The nobility or whatever, like the preps of the medieval ages that won't talk to anybody or bond with anybody because they already have a full wallet, we'll say, or a full outer shell. Okay, does that make sense? What? Okay, I thought you said something else. Okay, beggars, yes, that's better. Better than what was in my brain. All right, so atoms have a full valence shell or fill the electrons in the end, and they are chemically stable, meaning they aren't going to bond. Atoms that do not have their valence shells filled with electrons are chemically reactive. So pretty much everything else is somewhat reactive on the periodic table, right? Except for our noble gases. Okay. So hydrogen is very reactive. Now, it might not be the most reactive thing on the periodic table, but it is the smallest molecule and very abundant and likes to bond with everything. I always say it's the kind of like my hyperactive element on the periodic table. We're going to use hydrogen a lot this year. By the way, where do you find hydrogen and helium at? On the sun, right? I'm going to dig into your earth science knowledge. So we've got a lot of energy on the sun, right? And hydrogen, is it highly reactive? Yes. You guys remember making a hydrogen bomb? Yeah, we might do that just for fun. I know we've done it before. But on the sun, folks, the only reason the sun doesn't just disappear is because it's going through nuclear fission and fusion all at the same time between hydrogen and helium, becoming very stable and then splitting and becoming very unstable. It's like this. And in the process of doing that, does it take energy to make bonds? Does it take energy to break bonds? And it's all there. It's like in constant flux on the sun. Okay? And that's why we get radiation, all that energy coming off the sun. And then we use that energy on Earth, right, to excite pigments, right? Remember the light reaction, that pile of pigments on a leaf? We're going to talk more about this, but just think about how that's connected. And what happens at that pigment? Let's see if you really remember this. I heard water. We split water. Yeah. What's water made of? Hydrogen. It's kind of funny because you got all that hydrogen energy on the sun and it's exciting more hydrogen on Earth, and then you release the energy in those. So biology is all really just basic chemistry when you break it down. But basic. Nothing from the bottom. That's too heavy. That's in the Earth, right? That's not on the surface. So looking at Bohr models, folks, we call these, I don't even refer to these as Bohr models in chemistry. I just refer to them as the electron models, okay? Where are the electrons, okay? Little phone call here, pause. Oh, I'm going to ignore that for right now. Okay. So, what? It wasn't important. Okay, maybe. I would say if it's important, they'll come down. So looking at Bohr models for hydrogen, how many electrons does hydrogen have? 1. Does it have a full outer shell? No. How many does it want to be full? 2, right? So it needs how many more? 1. So how many times can it bond? Once. You guys are geniuses. Carbon has how many total electrons? Careful. 6. Okay, how many valence electrons? 4. How many times can it bond? 4 times. So it has a higher bonding capacity than hydrogen, right? Okay. All right. Do you guys understand how that works? Who can bond more, carbon or nitrogen? Carbon. How many times can nitrogen bond? 3 times. Okay. So we use the electron model, always putting 2 on the inside and up to 8 on the next one. If I get 8 in this second level, I got to go up 1, don't I? Like phosphorus. See, I have 2 here, and then 8 here, and then 1, 2, 3, 4, 5. So phosphorus is in the same family as nitrogen, right? So we come over here on the periodic table. We first talked about nitrogen has 5 in its outer shell. It's in the 5th family. Phosphorus does as well, right? It's just one has an extra level, that's all. But they still have those same bonding properties, okay? They both want to bond 3 times. So they're found bonding in similar ways. So if I give you any element, you should be able to do this. Okay? If you can't do this, you need to come see me at lunch. We'll sit down and we'll go through electron modeling. Okay? I don't know how you model electrons. Like how do you know which one's attractive and which one's not, and then which one do you know? Sorry. All right, you guys want to take a break? Okay. All right. I'm going to stop there after that very bad joke that no one got. I'll stop.